A neuron from scratch. To make a neuron from scratch, let's jump into a simple problem predicting a storm. We will try to predict a storm. If we have dark clouds and a sudden drop in temperature, then we predict that a storm is coming. This is a tabular data that represents dark clouds and temperature drop. This table represents the simple logical AND operation. A storm occurs only when both dark clouds and the temperature drop are present. As you know, weather prediction is pretty complex in reality. Here we are making this simple scenario where we shall predict that a storm will happen only if we have both dark clouds and a temperature drop. Now we can solve this problem with simple if else. We say we'll define a predict function which will have dark clouds and temperature as temperature drop. We will set our storm initially 0. We will check if dark clouds equals to 1 and temperature equals to 1 as well, then we set our storm to 1 and simply we will return storm from the function. Then we will try to predict, say predict for 1 and 1. As our data says, we will check for 1 0 0 1 and 0 0. Let's run it and we see we are getting our outputs correctly as the data says. And but we are doing machine learning here. We do not want to explicitly solve such problems. Why, you might ask? Well, there are problems that are extremely hard to program explicitly, and we use machine learning for solving those problems. For learning purposes, we are considering a simple problem here. Instead, we should write codes that can evaluate a given solution and then suggest a better solution. In practice, we start with random prediction and improve on that until we get a good enough prediction. And for this, we mimic the behavior of our brain's neuron. Neurons are like functions that take in multiple inputs and do some magic, and it outputs the result. A neuron simply puts weights on each input depending on the input's effect on the output. Then it accumulates all the weighted inputs. If the sum is greater than 1, then we shall output 1, else it's 0 as for the data. Why design a neuron like that? We shall know. As we have two inputs here, first of all we make a neuron class. We need to keep two weights for them, so we have created a neuron class, and necessary like self dot weight 1 and weight 2. So let's set for now, let's set weight 1 to 2 and weight 1 to 2 and weight 2 to 0.5. If you might ask, where do we get the values of weights? Well, that is machine learning. We will know in the last. So stick around. Let's get the predict function also. Predict function in our neuron class. Say and neuron class. From the neurons what do you say, behavior, we can see that a neuron simply puts weights on each input, so we will also put weights on each input. We say dark clouds multiplied with its weight, dark clouds multiplied with its weight 1. To access this, we need also call the self, and temperature is also multiplied with its weight. We will check if it is greater than 1 or not. If it is greater than 1, we will return stone 1, and else not. So let's make an object for the class. Neuron equals to neuron. Let's make it. We have made an object for the class. We will try to predict for our data for 1 0 0 1 and 0 0. Let's run it. Oops. We have two mistakes. Sorry, there is only one mistake here. The second prediction. From the data we can see that it should be 0, but it is returning 1. So let's change the weights. We will first of all set the weight both 3. Let's say run it, and we can see there are two mistakes now, second and third prediction. So let's change the weight again. Say 0.6 for the weight 1 and 0.8 for weight 2, and then run it again. So now we are getting the correct outputs. You can play with different other weights and check that if it gives correct results or not. So by now we do understand that simply by changing the weights we can adapt our prediction. Our prediction function for any input and output patterns. Therefore we need a learn function that takes two inputs and the output and does some magic again to change the weights accordingly. We are not going to change the weights manually. So let's define a learn function which will have these things, also the output. But first of all, let's initialize the weights randomly. So for that we need the random library, and the weight 1 should be random.random, and weight 2 should also be, say, random.random. And in the learn function, first we try to predict the result with the random weights that we have, and then we calculate the error. We calculate the error by subtracting the output. This is the output from subtracting our prediction from the actual result. So this is the actual result. The self.predict is the actual result, and this is the output. And finally we update our weights based on the inputs divided by 100. You might ask, why 100? Why divided with 100? We do not want to change the weights too much at a time. We wish to take small steps towards the solution, and because big steps often cause divergence, so we divide the error by 100 while updating the weights. And now the testing part. Let's test and train it. We will just copy and paste the code here. We have made an object that in this while loop we can see for testing we are running training as long as we get all the correct outputs. We are running this loop until we get all the correct outputs from our data. Say for 1 and 1 it has to be 1, and 0 0 0 for all the others. And we train by calling the learn function here. Let's try to predict. Print neuron.predict for the data on, let's say, 0, we say 0 1 and 0 and another 0. Let's run the cell, say 1 0 0 0. We have successfully coded an artificial neuron from scratch and trained it. Awesome. Let's make functions for training and testing, not like this. Alright, so let's copy that and delete these. We will first of all define our data here. Say 1 1 and 1, say comma, say 1 1 0 0 1 0, and it should be 0 0 0, and this should be 0 1 0. Yes, let's look at our data. 1 1 0 is 1 0 0 1 1 1. Yes, it's like that. Now let's make a training function. Let's make a training function. We will pass our neuron here, not the data obviously. Then for row in data, we will say neuron.learn row 0, row 1 and row 2, as we did before in the while loop. We will call another, make another function, say on testing, and we will return from it, say neuron.predict we say for row 0 and for row 1, and for row 1 in for data, for row in data, for row 1, row 0 and for row 1 we will predict the results. Let's make an object, neuron equals neuron, and then we say while true, we will say output is equals to run testing. It should be testing, not training. And then we will print the output. So if output equal row 2, yeah, it has to be row 2, because we have kept our outputs in row 2 for row in data. We will break the loop. Then let's also run the training phase, run training, and we will put neuron here. Let's run the code multiple times. Each time, let's run it again, not this one. Let's delete that. We'll say run again. See, at this time we didn't achieve our result in one go. We did it. It had to train itself. I mean, if you run the code multiple times, each time you will need a different number of steps to reach the solution. Let's try it again. See, this is because the random values used to initiate the weights. You might even, when we have already got the solution within only one step, you might as well. Alright, let's run it again. Sorry. Delete it and run it again. See, after many attempts, we got our result. So now let's play with some different data. Let's say for the second one, the output is 1. Now let's run it again and see, it took us so many times. It is taking more steps to reach the solution than before. We were like in 9 or 10 attempts, and now it's like more than 20. let's run the code again multiple times, so it's more now. um, let's change output for row column column 1, column 3, column 2. Let's run it and see, it took so many times to reach our output, so much. It's taking like, it should take it took so many steps and more steps than before. This is the this understanding is very useful to grasp the underlying mechanism of artificial neurons. Let's set all the outputs to 1 now and try it. Let's say 1 and 1. My computer might crash. Okay. My computer didn't crash, actually. Jupyter temporarily stopped sending output. Actually it is stuck in the while loop because we never get all correct outputs. The problem happens for the 4th row here, in our data, the 4th row here for 001, and it is easy to understand why. The input values are both 0, so no matter what our weight is, it is always 0, and multiplied by anything multiplied by 0 is 0. Thus the condition here, it never satisfies, so the loop is going on and on and on. Actually, let's set some threshold. We need to set some threshold to solve this problem. Actually, the threshold 1 in the condition, this is the threshold 1 in the condition is the problem here. Instead of 1, we could put a -1. Let's say it's -1 and see if it solves our problem. Let's run it. It solved our problem. It reached our output in 1 go. But then we will have issues with all the zeros with this condition. So we need to adjust the threshold accordingly as well. We can set a random value to the threshold. Let's make a threshold as well. Let's say self.t is equals to random.random, and we will compare it with the threshold itself. In the error part, it's all fine, but we need to adjust our threshold as well. Error divided by 100, and let's run it. We've run it. Let's stop it. Let's stop, and now we shall see. Everything is fine. It should be not plus, it should be plus. I'm sorry for that. Let's run now. You can see after many attempts we do reach our outputs here to our designated output. It's been amazing. We have successfully coded a neuron from scratch, an artificial neuron. And now let's get familiar with some mouthful ML terms. Bias. We simply call threshold TS bias. Here, this threshold is called bias in machine learning. Parameters. These all 3 are parameters. W1, W2 and T are called parameters. Variables that we learn through training. The act of selecting parameter is called parameterization. Model. After a model is after the training, we will have good values of W1 and W2 and the T, I mean the bias, that produce correct outputs. This set of values of parameters is called the model. The learning rate. While adjusting the parameters in the learn function, we divide the values by 100. You can also think of it as multiplying by 0.01. We call this 0.01 as a learning rate, often denoted by alpha. Learning rate is a very important hyperparameter value set by humans, not learned automatically through training, right? So the learning rate count, and now the gradient descent. The algorithm we ran in the learn function here, calculating the error and adjusting the parameters. Learn function to adjust the parameters is called gradient descent. So this is the gradient descent. The thing is here. More specifically, the variation we implemented is called stochastic something gradient descent, such SDG, not something stochastic gradient descent, SGD. Now regression, the whole iterative process of predicting. It is called regression. Calculating the error and then adjusting the parameters is called regression. The variant we used here is linear regression. Epochs, number of loops that were required in regression for reaching the correct outputs. These are the epochs. The above code considered only 2 inputs, but you can easily upgrade it for any number of inputs simply by using arrays. You should try at home. For this test case, run it, and you see we have only one neuron here, and it is been proved that one neuron can never solve the problem here. It is the XOR operation. We will need multiple neurons or neural networks to solve it. So yeah, we just started our journey. Good luck.